First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings. Today we're looking at the DIS method, and this is one of the coolest concepts, in my opinion, that we learn in calculus. This is all based on something called solids of revolution, where a three-dimensional object is formed by revolving something around the axes. There's various levels to this. Today's video, we're just going to look at revolving the function around the x-axis. In subsequent videos, we'll revolve it around other horizontal axes and also the y-axis and other vertical axes in videos to come. But for today's video, we're going to concentrate on solids of revolutions generated from revolving functions about the x-axis. So let me give you an idea of what we're talking about. So here I have a picture of a cone. So there's a cone with the vertex and the height and the radius and the slant height. Oh, that's not that important right now. But I want you to think of this cone being formulated or generated or produced by revolving some function around the x-axis. So to get a better picture of this, let's rotate this cone. So here the cone is rotated, and what I want you to think about is just look at this line. So this is just, say the equation of this function is y equals x, right? Y equals x is this line, and I got this line going from point A to point B. And if I rotate, so let's say this dashed line is the x-axis. Envision me rotating this line around the x-axis. If I rotate this line, so I'm just talking about this line here, I'm calling this the graph of y equals x. If I rotate this around the y-axis, it's going to generate this cone. Now, if it's difficult to see, if it's difficult to visualize that, let me use the following and see if I can make this picture a little more lucid. All right, so here I have the graph of y equals x. Y equals x is right here. And it's kind of like we're taking the integral. So it's showing you the area under the curve, which is significantly related to what we're doing here. We're mainly concerned, what we're going to be doing, and I haven't even mentioned this, is we're going to be finding volume of solids of revolution. So this is involved with volume. So it's, of course, it's very much related to area under the curve. So this is the graph of y equals x, and I got it going from 0 to 5. I mean, if you wanted to see it go farther, there you go, from 0 to 8, if that looks better to you. And what I'm going to do to give you a better picture is a simulation of me revolving this guy around the x-axis. And you see, when I revolve it around the x-axis, it presents this three-dimensional figure, which is a cone. And I can do this with any function. So it doesn't have to be a cone. There's a myriad of three-dimensional objects that can be produced by simply rotating a function, any function, about the x-axis, and really, of course, about any axis. But for today, we're going to be concentrated on revolving them around the x-axis. So, I mean, I can just take another function, say x squared, for instance. Okay, that's a bit much on there, so let's bring it in a little bit. And there's kind of how x squared looks revolved around the x-axis. I can take sine, say I take sine of x, and let me move it on to about the ending point around pi. And you see it gives you a little football looking figure there. And again, you know, you can think of any function you want, the square root of x. and you get that figure. So, you know, any function you want to think of, we can rotate it around the x-axis and generate some figure. So, and that's nice to do, and we can play with various functions and look at how their graphs look rotated about the x-axis. But the point today is concerned with finding the volume of these particular figures. So we want to look at finding the volume of these particular figures. And so let me go back to y equals x. And again, I said this was, you know, very much related to area under the curve. And so I'm going to show you how we found the area under the curve. So if you remember, we started with the Riemann sum with n number of rectangles, and then we found an infinite number. We used an infinite number of rectangles, which was represented in the definite integral. And we're going to do something similar here. So if you just look at the graph of y equals x, not rotated, and say I approximate the area, okay? I'm talking area right now. So say I approximate the area with rectangles, right? Now the deal is these guys are being revolved about the x-axis. So how would a rectangle look if I revolve it about the x-axis? So let me give a graph of something that would give me a rectangle. Let's say f of x equals 2. Okay, there's a rectangle, right? And let me make it a rectangle that's not that long. So there's a rectangle, correct? Now think about what happens is if I revolve a rectangle about the x-axis. So hopefully you could envision that we get a cylinder or a disc. So this is where the word disc in this method comes from, because within this cone, so I want to go back to this cone we generated. So in this cone that came from the function y equals x being revolved about the about the x-axis from 0 to whatever. Let's say right now I got it from 0 to 4. And I want to find the volume of this. Well, what I'm going to do is I'm going to slice this into cylinders. I'm going to slice it into cylinders to approximate the volume. And of course, I can slice it into n number of cylinders. But if I want the actual volume, I'm going to use an infinite number of cylinders. And that's going to require me to use a definite integral. But let's look at each particular cylinder. So I want to go back and again simulate a cylinder. I apologize for going back and forth. Just going to make it a little smaller, because when we do this method, we think of these as very small cylinders, very small disk. So the volume of a cylinder is pi r squared. The volume of a cylinder is pi r squared. So let me turn this into a rectangle real quick. So the question is, what is r? Now, again, this is created by the function, right? In this case, I'm just using the function f of x equals 2 just to show a particular cylinder. But the radius, so this is the radius in dark blue. The radius is actually the value of the function at a particular point. So the radius is actually the value of the particular function at a point. So let's go back to f of x equals x, the cone, okay? And think about an infinite number of disks. So there's a disk that can be formed at this value, etc., an infinite number of values, but the radius of that disk is the value of the function. So in this case, our radius r, so in the formula to find the volume of a cylinder, it's pi r squared h. The r is actually the function. It comes from evaluating the function at all the points between a and b. You know, if I'm going from a to b, at all the points in between a and b, which of course we can get from doing a definite integral. So The r squared is actually the function, which I'll call f of x. And the height, of course, we're doing an infinitesimal, we're doing an infinite number of rectangles. So in this case, the height would be our infinitesimal, or which we call dx. So if we look at the formula for finding the volume of a solid of revolution that's being revolved about the x-axis, from some function f of x being revolved about the x-axis from A to B, we'll find that volume using the following formula. And so this is the formula we will use. Now, again, remember the actual formula for a cylinder. And what we have done in this method is we have broken up the three-dimensional figure into an infinite number of cylinders or disk. The volume of a cylinder is pi r squared h. So there's our pi. So remember, there's always going to be a pi in this formula. And remember, r, the radius, is the function. So there's our r squared, the function squared, and our height is dx. We're using an infinite number of cylinders. So their height is an infinitesimal, and that's what we use the dx to. And for these, we're going to be defining the volume from some value as x goes from A to B. And those are the limits of our integral, our A to B right there. So I hope that rundown of how we get the formula made sense. And now let's go ahead and look at a couple of examples. All right, so there's our first example. May have outdone myself writing the instructions. I could have shortened some of this, but I'll go ahead and read what's written. So it says, find the volume of the solid formed by revolving the region bounded by the graph of f of x, which is the square root of sine x, and the x-axis about the x-axis on 0 to pi. And so, of course, this can be written a lot of ways. Sometimes they'll say the region bounded by, f of x, and they'll say the x-axis, and they'll say, and the lines say x equals 0 and x equals pi. Or sometimes the mention of the function and the x-axis, the x-axis part is not mentioned. So this could be worded, a variety of ways. But essentially, our function is the square root of sine x, and we're going to revolve it around about the x-axis, and we're going to find the volume as x goes from 0 to pi. Okay, so again, this is our formula. So the volume in this case is going to be pi times the integral from 0 to pi of f of x, which is the square root of sine x squared dx. So that's the formula we're going to use. And there I have that. I always have that proclivity of writing to the side. It normally only happens when I begin doing the math. You can see when I wrote the instructions, it's fairly parallel with the paper, but when I start doing the math, for some reason, it gets that lean to it. But let's go ahead and finish this off. So we can square this. So this volume, I'm going to try to make this straight, even though I have to tilt the page as I write. So of course, the square root of sine x squared is just sine x. So we're simply integrating pi times, and always remember to do the pi. So in this formula, it's pi times the integral from A to B of f of x squared. So sometimes a lot of people forget that pi. So don't forget the pi. So we have pi times the integral from 0 to pi of sine x. So we can go ahead and integrate. So what is the integral of sine x? Is it cosine x or is it negative cosine x? And so hopefully you said negative cosine x. So this is pi times negative cosine x to be evaluated from 0 to pi. All right. So cosine of pi is -1. Cosine of pi is -1. That's negative, so that's going to make it +1 minus cosine of 0 is 1. So it's minus -1. It's cosine of 0 is 1. There's a minus sign, so that makes it -1. And 1 minus -1 is 2 times pi. So our answer is 2 pi. Okay, let's do one more example. All right, so here's example number 2, and it says we're going to find the volume of the solid formed by revolving. I missed the word formed. Let me make a quick addendum. And I kind of truncated the directions a little bit. You guys kind of get the drift. I don't have to be as maybe specific as I should on these directions. So find the volume of the solid formed by revolving f of x, which is 4 minus x squared, about the x-axis on -2 to 2. And initially when doing these problems, and you can think about this, of course, as a graph of a downward facing parabola whose vertex is at 0, 4, and who hits the x-axis at -2 and +2. I think in these initial problems, it's always good to kind of to look at how this solid of revolution looks when generated. I didn't do it with the first function. The first function kind of looks like a football, just as the graph of sine x itself kind of looks like a football, but the square root of sine x also kind of looks like a football when revolved about the y-axis. So I'm just going to quickly take a look at both the first function and the second function, how they look when revolved, and then we'll go ahead and find the volume. All right, so let's go to the first function we did. That was the square root of sine x, and we went from 0 to pi. Well, so maybe 3.1 is better than 3.2, and so there's the guy there. Again, it's a football looking object, and so very beautiful. And the one we're about to do now is 4 minus x squared. And this one we're going from -2 to 2. And that's kind of how that shape looks. So this is the base cross section, if you will. So that's kind of how it looks. A beautiful looking figure. So let's go ahead and figure out its volume. All right, so this is a very simple formula. So again, the formula is pi times the integral from a to b of f of x squared. So for this case, it's going to be pi times the integral from -2 to 2 of 4 minus x squared dx. So that's what we're going to find. And it looks fairly straight. I'm getting better. So I'm going to go ahead and square this. So I'm not integrating yet. I'm just squaring the given function, -2 to 2. So if I square it, that will be x to the 4th minus 8x squared plus 16 dx. So this is what I'm going to integrate again, and all I did is just square this particular function to be ready to integrate. So now I'm ready to integrate. And so this is pi times x to the 5th over 5 minus 8x cubed over 3 plus 16x to be evaluated from -2 to 2. All right, so that's what we have there. So we're going to plug in 2 and then plug in -2 and then subtract those guys. Okay, so let's plug in 2 and see what we get. I'm going to put the function here so I can see it. All right, so when I plug in 2 to the 5th is 32. So that's going to be, and there's a pi here. So let's do this. So I plug in 2 to the 5th is 32. So that's going to be 32 over 5. 2 cubed is 8 times 8 is 64 minus 64 over 3, and 2 times 16 is 32 plus 32. All right, that's what I get in for plugging in +2 minus, now I'm going to plug in -2. So -2 to the 5th is -32 over 5 And negative 2 cubed is negative 8 times 8 is negative 64. But with that minus sign gives it a positive 64 over 3. And negative 2 times 16 is negative 32. So what we received were the same numbers that we got from when we plugged in positive 2, but just opposite signs. So we got 32 over 5, so negative 32 over 5, negative 64 over 3, positive 64 over 3, positive 32, negative 32. And that, of course, happened because they were polynomials raised to an odd power. If they were polynomials raised to an even power, there wouldn't be a change of signs. But since these are opposite signs and these guys are being subtracted, what's going to happen is all of these values are going to double. So 35, excuse me, let me put the pi here. So 32 over 5 minus negative 32 over 5 is 64 over 5. And negative 64 over 3 minus 64 over 3 is minus 128 over 3. And 32 minus negative 32 is 64. All right, so we need to add all these guys up, and there I started leaning again. It was just a matter of time. We need to find a common denominator. That common denominator would be 15. So pi, so I'm going to really concentrate on making this straight. So the 64 over 5, I'm going to multiply top and bottom by 3. So that's 192 over 15 minus the 128 over 3. I'm going to multiply top and bottom by 5. So that's 640 over 15. And the 64, I'm going to multiply by 15. That one I'm going to need to work out a little bit. So 64 times 15, that's 20, that's 32, and that's 64, 960. So 960 over 15. All right, now let's do our arithmetic. So if we just take these two guys, that's going to be 320 over 15. So these two gave me 320. There's a minus sign there, of course. So 320 and 192 is 512. So 512. So 512 pi over 15. And I don't think that can be reduced. 512 is 8 cubed, 64 times 8. And I don't think it has any factors with 15. So that would be our final answer, 512 pi over 15. All right, that's our first of several videos over the disk method and finding the volume of solids of revolution. We'll see you next time.
Specialize in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe-to-toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.